And this morning we're going to have a discussion about rapid tooling involving the merging really of additive manufacturing and subtractive manufacturing. When I say additive manufacturing, of course I'm referring to 3D printing. Talk about the different tooling applications and how they apply. Before we get started, I want to talk just briefly about D3 Technologies. D3 Technologies actually is a consulting company, and we partner with manufacturers. We help you as manufacturers with getting your products to market faster, maybe by leveraging various engineering technologies, design technologies, data management, and of course 3D printing technologies and 3D scanning technologies. We represent both 3D systems as well as 3D platform in the terms of 3D printing, and then of course we represent the 3D systems, 3D scanning technologies as well. So really, when you talk about 3D printing falls into four basic categories. First, communication, which is really what 3D printing is known for. A lot of times people think that that's their only method for being able to do 3D printing, which is being able to print concept models. Secondly, validation. A lot of times people use 3D printing for validating, making sure that they can test it, whether it's running liquids through it or running air through something, or just making sure it's got the right form or fit. Thirdly, pre-production models. So this is what we're going to focus on today, rapid tooling, how people can use rapid tooling technology or applications in the 3D printing technology. And then lastly, end-use parts. A lot of 3D printing is being done today with end-use parts in many different applications. So let's start out with some of these rapid tooling applications. First of all, as you probably know, 3D printing really is revolutionizing the tool making market. As product development kind of converges on that final design, attention rapidly turns to the whole manufacturing startup. And really this stage often involves a big investment in the tooling of jigs and fixtures necessary to manufacture those new products. So at this stage of rapid tooling, the supply chain expands with purchase commitments for some of that raw material, and the lead time for these required items can really stretch out your time to market. So 3D printing in a variety of ways really does help kind of reduce that investment risk and shorten your time to production. So here are the areas that we're going to talk about today for rapid tooling, and I'm hopeful that some of these will apply in your world. Not all of them do, I'm sure, but I'm hoping that at least one, if not two of these will. So for those processes, 3D printing can really provide the master pattern and sometimes even the mold itself. With RTV molding, 3D printed patterns can be printed in just a few hours, and they can be really accurate and have a lot of details along with some great surface finish, which is really critical as you're doing RTV. Hydroforming creates really a tool in just a few hours as well with great surface finish and sharp edges. For thicker metal pieces, you can also 3D print the negative mold to pour your iron filled epoxy. And then of course thermoforming is another example, fiber layup. You can create a tool in just a few hours and have some really high temperatures involved in that process. So let's focus now on RTV molding, and I'm going to talk about some case studies and how this technology works. So if you take a look, this is kind of your background info, and I'm sure some of this you already know if you're doing some of this, but your first step is creating a stereolithography master, and stereolithography is just one of the technologies that 3D System actually invented out there. So first you're going to create your master, then you're going to pour your rubber. Step 3, you're going to do your cast urethane. Then you're going to autoclave that. and then you're actually going to demold that part and then clean the flash off of the part itself. So that's kind of as a round piece, what can be accomplished with RTV. This happens to be an example of a great application of Coca-Cola Company and APP, which happens to be a division of 3D Systems, their Quick Parts division, and how we work together to make this happen for them. So their whole challenge was really redesigning, prototyping, casting, and even decorating and shipping about 150 cast urethane bottle carriers for the Powerade to be used as a promotional item in the 2014 FIFA World Cup. And they also had to try to complete this within 30 days. So with the combination of using these 3D Systems SLA printing or stereolithography printing, they were actually able to do that even with a couple of days to spare, believe it or not. So once a few of the minor changes were made, the team made a full-scale SLA or stereolithography part out of resin material in our SLA printer, which took about 15 hours for 2 parts each batch. And then these were used as a final fit check part and mold masters for the silicon molding and casting process. We actually printed about 6 mold masters in less than 2 days, from which the silicone molds, of course, were created for the production phase of the bottle carrier. And then after that, then they actually, each tool was there to produce about 50 quality parts and ready to start the assembling process. So just to let you know, they actually were able to cast and assemble about 300 cast urethane parts into finished carriers. So this is another example. This is a company called Redfish, and Redfish actually develops electronic devices that function in tandem with the Apple iPhone, the iPad, and the iPod Touch. So Redfish's instrument, which is the IDFM device, it's a digital multimeter that wirelessly transmits voltage and current for enhancing their visualization for data sharing and data logging. Well, their big challenge with Redfish was that they had created an initial design for this IDVM device, but they needed functional prototypes and production sourcing. So Quick Parts, again, which is a division of 3D Systems, produced the initial black SLA prototype for the top and bottom of that design case. And then from there, design revisions were implemented. Then Quick Parts did a pre-production cast urethane part that allowed Redfish to further test the design, the color, the functionality, and even the finished texture. So that just kind of gives you a good idea as to what they're doing with cast urethane. This is another example of Magellan Technology out of Australia. In their case, their big challenge was a new smart document tray reader concept that needed prototyping to production solution. So they actually were using 3D Systems plastic jet printing process, and they used a variety of colors for fit and function testing. And believe it or not, even after that whole thing was done, 3D Systems then built production display models through what we call our quick cast urethane or RTV mold process to allow them to demonstrate those at their trade shows. This company is called PediaVision. So they're actually a medical device company that provides vision assessment technology to adults and children. And so their whole challenge was the demand for PediaVision's advanced vision screening device, which is called SPOT. and it was actually outpacing traditional manufacturing techniques that they were using today. So they had to fill that gap between the early stage development process and the hard tooling. And what they actually did was 3D Systems was able to test production quality prototypes months before the traditional tooling would allow. Within 7 days, PediaVision received their prototypes from us, and they were able to test with production material and production tolerances really prior to going to hard tooling. And then the rapid prototyping allowed them to compress their schedule by about 3 to 6 months. So the quick plastic cast urethane process combined with 3D Systems knowledge allowed them to reach their production much sooner and reduce their tooling costs as well. So I want to go into a little bit with hydroforming and just talk about that just briefly. For those of you that don't know much about hydroforming, this is kind of the process that you go through, and that is a forming tool is placed inside a hydraulic chamber with a workpiece and then a pre-stamped metal piece. The chamber closes, creates slight pressure, and then from there you've got clearly the pressure is increased to about 5,000 psi, forcing a liquid-filled bladder, and then the pressure is actually released from there to reveal the formed metal part. So this is an example of a same-day hydroforming tool. In this case, the die mold was actually printed in 6 hours within our multi-jet printing technology of 3D. There was no sign of wear after 100 pieces were formed. So, and the advantage of this is that with the multi-jet printing technology of 3D Systems, you really get great surface finish, and it's a very low investment cost. This tool actually was able to withstand extreme pressures of up to about 5,000 psi for hundreds of runs. That's the beauty of this. I'm going to just kind of run through. I want to show you this process that we went through for the same-day hydroforming tool on the 3D Systems multi-jet printing. The beauty of it is you can immediately use this hydroforming tool the same day. So they're placing the 3D printed part, and now they're adding the sheet metal, and they're going to start that hydroforming process. So now the gentleman's going to kind of check that finished part, make sure that it's formed properly, and then he'll remove that 3D printed part from the forming. So you can repeat that process as many times as you need to get that hydroforming. So I just wanted to kind of show you how you can do your same-day tooling needs and start the whole process with some of our technology. This is an example for negative hydroforming molds. So for thicker metal pieces, you can create a mold and then pour an epoxy tool for higher pressure hydroforming runs. The beauty of our technology is that you've got that excellent surface finish and accuracy, allows that epoxy release to happen quite seamlessly. This is just another example of a die mold that was produced for hydroforming. Again, it could be done hundreds of times. I want to go a little bit further into the thermoforming, vacuum thermoforming, and fiber layup processes. Again, I don't know if all of these apply to you, but I think it's just good information to know how 3D printing can help advance time and certainly cut your costs. For those of you that don't know much about thermoforming process, this just kind of shows you a little process of how the positive mold, negative mold with the heated plastic sheet in between, and it allows a little bit of air escape there. So really, if you guys thought that until now mass production is not achievable by 3D printing, Well, let me just kind of ring the bell here and let you know that this is in fact happening all day long. Align Technology, which is a partner with 3D Systems, and they use our technology certainly for producing these dental aligners to the tune of 17 million per year, with the help, of course, our 3D printing technologies that we provide them. Their challenge initially was an orthodontic product like Invisalign braces requires from about 16 to 40 sequential appliances per arch. So manual fabrication of many appliances would just be really expensive, and it would be very difficult for them to maintain the required accuracy. So their solution was, instead, Align Technology came to us, and now they're using our stereolithography, our SLA technology, to create its reference models. So now a dental impression can be taken by your local dentist, and then it's scanned, and then the sequential steps are taken to straighten the teeth as defined, that are typically between 30 and 40 of them. Each stage of the treatment is 3D printed in a full factory floor of our SLA printers, and then they are loaded into an automated aligner forming system that kind of heats, forms, and laser marks the sheet plastic over each plastic model. So just some good information about how mass production is actually being worked with our 3D printers today. So I want to talk a moment about fiber layup and vacuum forming. Again, this just kind of shows you how the process works to shape thin sheets of thermoplastics. So with all of 3D Systems printing technologies, we have the capability to print vacuum forming molds. And so this is going to be an example I'm going to show you here in a moment. And this test is really focusing on the use of our, what we call FDM, using the ABS material, our color jet printing technology, our multi-jet printing technology, and our stereolithography technology to print large and small molds for short-run production of form parts, and as well even some custom one-offs or other types of prototypes. So hopefully that kind of gave you a good idea as to how some of the vacuum forming happens. I think it's a very fun process, needless to say. Want to get on into another example. This is Bell Helicopter. which is a great customer of ours as well. And their challenge was that they had deadlines for getting helicopter parts out the door, and they had to get them to the test facilities on time. So if they missed that window of opportunity for a test, it might be a year or more before they could reschedule another one. For the glare shield project, they actually required about 9 different test specimens in 3 different thicknesses. So the solution, of course, in this situation is that Bell Helicopter actually uses our stereolithography technology, and they use a high temperature SLA material to make a vacuum mold and layup tooling. So the process begins with, of course, their CAD file, which is then sent to the 3D Systems SLA printer. Then a physical model or tool can then function as a pattern to form the parts out of other materials such as polycarbs or foam or carbon fiber using a high temperature process. So to build the glare shield with conventional tooling, taken like months, 6 months to a year. So instead they finished the project in only 2 months, and they were really impressed with the accuracy of the stereolithography, as they really deal with tolerances that are tight at about 2 to 3 thousandths. So the material used to make that tool had to be able to also withstand a high temperature of about 392 degrees Fahrenheit. So I want to talk just a second about injection molding and how injection molding can be used with 3D printing today. I think everybody probably knows, but injection molding is used to create a lot of things: packaging, Game Boys, small tables, storage containers, and it's really one of the most common method of manufacturing parts. It's really great for producing high volumes of the same object. So this is a courtesy of BuyLink, a customer that in their case, their whole case of being able to do injection molding was really from a time saving. So an injection mold that they were able to do in 12 hours on 3D printers versus normally it took them 2 to 3 weeks for a metal mold, and that metal mold cost them about $6,000 to $7,000. So with 4 printed mold iterations in 3D printing in only 6 days, you can modify the parts, improve the products without any hard tooling costs and lead times. Not to mention, these materials can withstand upwards of 10 tons of pressure, injecting temperatures as high as about 335 Celsius. So obviously they're able to get high quality actual part productions with tiny features and complex shapes that are much easier with the applications here. So the next example here I've got is Parker Hannifin, and they're a leader in motion and control technologies today. So stereolithography printing is something that they brought in-house, and they are using that to print molds for use in the manufacture of urethane filter seals. With stereolithography, they were able to get that high polished surface finish, which is really critical for mold release and also for their effective filter seals. The beauty of that technology for them is that, you know what, whenever a mold wore out, they simply printed a new one. Here's another example of molds. Molds are actually produced with our direct metal printing technology, and you see this a lot with our tire manufacturers. Obviously, you can do sipes and tire molds here with the metals. In this case, they're able to get about 150 micron wall thickness, and they're using various types of material like 17-4, etc. Here's another example for specialized tooling. In this case, this was done on the 3D Systems direct metal printer, and for these 12 inserts, it took about 50 hours to produce, but if you notice, you get really smooth vertical walls with a special build style. Those are built on about a 45-degree angle. So there's undercuts without any supports in our metal printing. This is, I want to get into a little bit with the molded pulp. Again, not sure if you guys do this, but something worth taking a look at. Just for a little background info, you'll know that molded pulp or fiber is a packaging material from recycled newsprint or paperboard, and it's really used a lot in the food service trays and end caps and so forth. So molded pulp is less expensive than other methods, and it's also considered a sustainable packaging as well. So again, there's a lot of tooling applications that can be used for that. Getting into jigs and fixtures, I think everybody probably knows what a jig and fixture is, but a fixture is a work holding or supporting device used in the manufacturing, and a jig is a custom-made tool used to control the location and or maybe the motion of another tool. This is a good case study for Citizen, and in their case, they prior to this, they were actually relying in-house, doing their prototyping in-house and using CNC lathes to machine and create mock-ups of their final watch designs and assembly jigs. But because it was so costly and it was took so much time, they wanted to bring 3D printing in. So they brought in multi-jet printing technology, and their whole challenge was really improving that assembly jig, which typically took about a 20 to a 30-day process. So it was really costly and took a lot of time. So they were able to invent new assembly jigs, and with that printer they took and transformed their 20 or 30-day process into an overnight production, which now is really becoming a very seamless transition. So I want to get into a little bit with some Foundry applications. Casting processes that really do benefit from 3D printing is investment casting. There's a lot of direct wax patterns that you can get, plaster casting, sand casting, spin casting, and die casting. So again, I don't know if all of these apply to you, but maybe some of these might, so I'm going to talk about a couple of case studies that make sense in each one of these categories. So I want to go into investment casting first. These are using real wax patterns. So 3D Systems actually has a wax printer that allows you to print out these wax patterns, and this happens to be a company in Romania. They're a Romanian gas industry company, and they had a project where they needed to design, test, and produce new and simpler pressure regulators. So the initially CNC machined housing prototype really wasn't fitting their assembly properly, just because it was very complex, as you can tell, and it had a lot of detail. So their whole solution was using our wax printer and as casting patterns to produce the aluminum alloy test housings. And then after the casting process, they used a CNC machine for the assembly planes to get the threads. And they actually took, from the CAD file to the final test part for the project, it only took 12 days. So really saved them a lot of time and money. This is another example of a company called Turbine Technologies, and they manufacture turbine components, of course. In their case, from design to wax pattern, they were able to go up to 70 times faster and about 10 times cheaper using the wax patterns. Their traditional tooling took them up to 5 weeks and more than $20,000. Whereas with the 3D printing in the wax, they were able to do it overnight and for less than $2,000. So again, it was huge in terms of allowing them to do several tests and produce their parts accurately and certainly much less expensive. This is another company called Honda, which I think we're all familiar with, they were able to reduce their design to manufacturing by 4 weeks by being able to do more design iterations. So there was really a great application for them to be able to turn some of their production vehicles into some various race engines in a very short amount of time. I'm going to talk a little bit about investment casting using our quick cast patterns. So what is an SLA quick cast? It's a special printing style that requires less material to be burned out during casting. You can make lightweight patterns. Its internal structure is about 70 to 90% hollow. This is an example of TechCast here in the U.S. and they're really a supplier of high-quality castings up to 350 pounds of their pump impeller castings, so they're huge. Obviously, they're not small at all. Their challenge was tooling costs, especially for these large impellers. They could be really high, very expensive, and the lead times were very long. So oftentimes the tool required cores, either soluble or ceramic. So to create those internal flow paths, it required at least a couple of tools to be built, and it really wasn't practical for repeating or modifying that. So their solution was a quick cast pattern, and quick cast really allowed them to do that in a fraction amount of the time of what tooling costs would be, so that they were available in less than a week versus originally about 3 months. This is another example of Raytheon, again using quick cast patterns to eliminate tooling for quick flight testing and changes on the fly. This really reduced their part count. Their missile spine was built in about 6 pieces and bonded with the same SLA stereolithography polymer. The one-piece casting of the rear section that was printed in an SLA part actually replaces 13 individual pieces and 451 rivets and screws. So this example really accentuates how accuracy and scalable flexibility of stereolithography for both complex and large assemblies. And again, this is another company, Lotus. So in this case, they used our stereolithography and quick cast application. There was no negative implication, no extra cost to add all these complex details. And there's also some conformal cooling channels running through that housing. So that really is impossible to do with your original traditional techniques. And I just want to talk about a couple of things, and then that should be it, and that's investment casting and spin casting. Again, here's a little example of accuracy and fine detail for wax patterns for spin casting. Sand casting, I think everybody kind of knows. Here's the process that you go through for your whole sand cast process, for those of you that don't know. And here's an example of a company called Advanced Tooling, where they actually do validation of our stereolithography technology with sand casting process to, again, help reduce those costs and time. Tests had been done on the production of the bracket for an automotive air conditioning system, and then the bracket was successfully casted in aluminum, which cut down their costs and time. And it also gave them a high level of accuracy and detail. Again, sand casting, direct metal printing that we offer also allows you to print directly from ceramic or alumina cores that can be easily dissolved with chemicals. Die casting. Again, just some quick tips about die casting and quickly produce some precision tooling for complex parts in aluminum, magnesium, or zinc. And again, you get great tolerances, surface quality, and speed certainly. So I'm hoping that this gave you a little bit of information about some of the different methods and applications that are used in tooling and 3D printing today. Certainly feel free to reach out to me if you have any questions or if I can help provide you with any information from this cast. And you can certainly reach us at 877-731-7171. Thanks, you guys, and have a great day.